Have you ever wondered how everything began, the origin of the universe perhaps? Well, there's a theory about that and it's called the Big Bang. It's not just a catchy name for a popular TV show but the widely accepted explanation for the birth of our universe. Imagine, if you will, all the matter, energy, space and even time compressed into an infinitely small and dense point known as singularity. Suddenly, about 13.8 billion years ago, a colossal explosion occurred. This explosion, or rather expansion, is what we call the Big Bang. In this video we'll traverse the cosmic landscape discussing fascinating concepts such as the singularity, cosmic inflation, and cosmic microwave background radiation. These concepts might sound intimidating, but don't worry, we'll break them down into digestible bits. So, buckle up for a journey back to the very beginning of time and space. Imagine all matter, energy, space, and time crammed into a point of infinite density. This is what we call a singularity. Let's take a moment to grasp the enormity of this concept. A singularity, a point of infinite density, is where our understanding of the universe begins. It's a state so dense, so intense that our conventional laws of physics just can't handle it. They break down, they crumble. Now you might be wondering, how is it possible for everything we know, the stars, the galaxies, the vastness of space and the ticking of time, to be compressed into a single point? But that's the beauty of a singularity. It defies our everyday comprehension. In this singularity, all the matter and energy that now fills the cosmos was squeezed into a space so tiny that it would make a grain of sand look colossal. And time? Time as we know it didn't exist, it was all just there. The universe, in its entirety, was a singularity. But studying this state of singularity is like trying to read in pitch darkness. The tools we have at our disposal, the laws of physics, are rendered useless. They can't penetrate the singularity's unimaginably dense heart. So we're left with theories, hypotheses, and mathematical models. Some scientists propose that quantum effects, the rules governing the tiniest particles in the universe, might help us understand the singularity. That's where theories like quantum gravity come into play. But even these theories are in their infancy, and there's much we still don't know. Despite the challenges, we push on, driven by our inherent curiosity and our desire to understand our cosmic origins. We look to the singularity, to the state of the universe before the Big Bang, because we know that's where our story begins. So picture this singularity once more, a point of infinite density, where matter, energy, space, and time are indistinguishable. It's mind-boggling, it's fascinating, and it's at the very edge of our understanding. In this almost incomprehensible state, the universe was born. Suddenly, in a moment of cosmic drama, the universe began to expand. This was not an explosion, as we might think of it, but rather an expansion. Picture a balloon inflating. As it gets larger, every point on its surface gets farther away from every other point. This is what happened at the dawn of our universe. In those first fractions of a second, the universe was a hot, dense point of pure energy. There was no space, no time, as we know it. All four fundamental forces of physics, gravity, electromagnetism, and the strong and weak nuclear forces, were unified in a state of perfect symmetry. Then, in a flash, everything changed. This symmetry broke down as the universe cooled, leading to what we call the Big Bang. But let's be clear, the Big Bang was not an explosion in space. Instead, it was the rapid expansion of space itself. This is a critical point to understand. The Big Bang didn't happen at a specific point in space because there was no space before the Big Bang. It happened everywhere at once because it was space itself that was expanding. As the universe expanded, it also cooled. This cooling allowed for the formation of particles like quarks, which eventually combined to form protons and neutrons. These particles then came together to form atoms, the building blocks of matter. We're talking about a period of less than 3 minutes after the Big Bang, and yet the foundations for everything we see around us today were already being laid. This process of expansion and cooling continued, giving rise to the universe as we know it. Over billions of years, the atoms formed during the Big Bang would coalesce into stars, galaxies, planets, and eventually life itself. So when we talk about the Big Bang, we're not talking about a single cataclysmic event. Instead, we're talking about a process of creation, of expansion and cooling that continues to this day. It's a story that's still being written, a cosmic drama that's still unfolding. This was the fiery birth of our universe. Following the Big Bang, the universe underwent a period of rapid expansion known as cosmic inflation. Now, this isn't inflation in the way we typically think of it. like a balloon being filled with air. No, this was an exponential growth spurt where the universe grew by a factor of at least 1 followed by 26 zeros in less than a blink of an eye. It's an almost unimaginable scale of growth that's difficult to wrap our heads around. Cosmic inflation is not just a fanciful idea, it's a theory that was proposed to solve some of the biggest conundrums in the Big Bang theory. For instance, the flatness problem, which questions why the universe appears to be remarkably flat and not curved. Or the horizon problem, which puzzles over why distant parts of the universe, which should never have been in contact, have the same temperature. The inflationary model elegantly addresses these issues by proposing that the universe experienced this mind-boggling expansion, smoothing out any initial curvature and allowing far-flung regions to be in causal contact. The evidence that supports this theory is imprinted in the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this radiation, like the ripples on a pond, are thought to be the fingerprints of quantum fluctuations in the early universe, magnified to cosmic scales by inflation. But cosmic inflation did more than just solve problems and leave fingerprints. It also set the stage for the formation of galaxies, clusters, and superclusters. It's like the universe was a loaf of bread dough, and inflation was the yeast that caused it to rise, filling it with bubbles that would become the large-scale structure we see today. So, while it may be difficult to comprehend, cosmic inflation is a pivotal part of our understanding of the universe's history. It's a testament to the power of theoretical physics and our unending quest to understand our cosmic origins. Cosmic inflation set the stage for the universe as we know it today. The universe has a baby picture, and it's called the cosmic microwave background. Imagine you've just walked into a room where a party just ended. You didn't witness the festivities, but the popped balloons, streamers, and half-eaten cake give you clues about what happened. This is essentially what astronomers are doing when they study the cosmic microwave background, or CMB. The CMB is the radiation left over from the Big Bang, akin to the remnants of a cosmic party that occurred nearly 14 billion years ago. This radiation is not just any kind of radiation, it's microwave radiation, which is why we call it the cosmic microwave background. It's everywhere, filling every nook and cranny of the universe. It's even passing through you right now. But don't worry, it's not harmful. In fact, it's incredibly weak, which is why it took until the mid-20th century for us to detect it. The CMB is a snapshot of the universe when it was just 380,000 years old, a mere blink of an eye on the cosmic timescale. At that time, the universe had cooled down enough for atoms to form, which allowed light to travel freely for the first time. This light is what we now see as the CMB. The cosmic microwave background is incredibly uniform, with only tiny fluctuations in temperature. These fluctuations are important because they give us clues about the early universe and its density. They also provide compelling evidence for the Big Bang theory. If the universe had always existed in its current state, we wouldn't expect to see this kind of radiation. But the Big Bang theory predicted it. Studying the CMB is like piecing together a cosmic jigsaw puzzle. Each tiny fluctuation is a piece of the puzzle, helping us to build a picture of the universe's infancy. And the picture that's emerging is one of a hot, dense universe that rapidly expanded in a Big Bang. It's like the universe left us a message in a cosmic time capsule. Fast forward 13.8 billion years, and here we are. From an infinitesimal point of singularity, the universe has unfurled into an expansive, ever-widening cosmic tapestry. A tapestry woven with galaxies, stars, planets, and even life itself. An extraordinary testament to the power and legacy of the Big Bang. The aftermath of that monumental event has been nothing short of awe-inspiring. The universe, once a hot, dense, uniform soup of particles, gradually cooled and expanded. This allowed particles to combine, forming atoms, the building blocks of matter. As the universe continued to expand and cool, atoms clumped together under the influence of gravity, forming stars. These celestial bodies then grouped together to form galaxies, each a sparkling microcosm of the universe. But the universe's evolution didn't stop there. Stars, through their fiery fusion reactions, created heavier elements. When these stars reached the end of their lifetimes and exploded in spectacular supernovae, they scattered these elements across the universe. This cosmic dust, enriched with elements like carbon, nitrogen, and oxygen, became the raw materials for new stars, and even planets. And, on at least one of those planets, the conditions were just right for life to emerge. The universe, however, is far from static. It's still expanding, still evolving. Galaxies are drifting farther apart, the universe is becoming more diffuse. But don't worry. This process is happening over billions of years. It's part of the cosmic narrative that began with the Big Bang, and it's a story that's far from over. So the next time you gaze at the night sky, remember that each star, each galaxy, is a part of the Big Bang's legacy. They're tangible evidence of the universe's spectacular birth and its ongoing evolution. They're reminders of our place in this grand cosmic story. From a singularity to a vast, ever-expanding cosmos, the universe has come a long way. And we, as curious observers, are privileged to bear witness to its magnificent journey. The Big Bang Theory gives us a glimpse into the earliest moments of the universe. It's a fascinating narrative that weaves together the threads of space and time, of matter and energy, into a tapestry of cosmic history. This theory, the Big Bang, provides the foundation for our understanding of the universe's birth. It posits that our cosmos started as an infinitely small, hot, and dense point, a singularity, which then expanded rapidly. This was not an explosion in the conventional sense, but rather an expansion of space itself, an explosion of space and time. In the blink of an eye, this expansion caused the universe to inflate from a minuscule point to an entity of cosmic proportions. As the universe cooled and expanded further, particles began to form, eventually leading to the creation of atoms, stars, galaxies, and everything we see around us today. The Big Bang Theory also leaves us with a legacy, an afterglow, if you will. This cosmic microwave background radiation, a faint whisper from the universe's infancy, is a testament to the Big Bang and provides us with tangible evidence of this phenomenal event. It's important to remember that the Big Bang Theory is not just about the past, it also gives us insights into the future of our universe. It suggests that the universe will continue to expand, with galaxies moving further away from each other. The Big Bang Theory is more than just a scientific theory, it's a narrative about our cosmic origins. It tells us where we came from, where we're heading, and most importantly, it shows us our place in this expansive universe. It's a story of cosmic proportions, a story of everything that is, was, and will be.